When Isaac Newton was awarded his Master of Arts in 1668 from Cambridge University's Trinity College, he was in possession of not almost all of humanity's shared mathematical knowledge. He had extended this knowledge to be able to deal with infinities and infinitesimals, and thus understand change in a truly quantitative way for the first time. He had glimpsed a way to treat motion and force, and for the first time had a pretty good idea of what drew objects to the Earth and held the planets in their orbits around the Sun. Yet, as he received the robes of his new status, almost no one knew of his discoveries and innovations in mathematics. Only the man whose place he would one day take at Cambridge had seen some hint of the fullness of the fluxional calculus, and just a few of the other mathematically inclined faculties had read his essay on the topic. None knew of his work on gravitation or his attempts to tease from nature an understanding of motion. So too in the case of his experiments on light, color, and optics. All of these advances had been made in solitude and seclusion up in Lincolnshire with no one there to witness them. Yet scrawled through the pages of his waste book is line after line in spidery script. Many of the entries began as the copying of passages from other books, as if Newton was in dialogue with them. But in each case the transcription turns into response and speculation, and then seamlessly into original thought and progress in making something new. At times, these dense blocks of text reach a conclusion, an insight that is new and daring. In other cases, they meander to an end with no resolution other than to recognize that there is more thought to be given. In the area of optics, there is data and diagram scattered through the text, as a way to support the new conclusions being drawn regarding the nature of color and light brought forth from the prism and beams of light coaxed through small holes and slits in the drapery of his study. When he returned to Cambridge, Newton had two pieces of work that were complete: the calculus and his ideas on optics. And yet he published neither, nor did he share his ideas on force and motion. The math was written in an essay, read to those interested at the college, and shared through a few letters from Isaac Barrow to others, but never printed and distributed. In optics, he continued his work in his chambers and reached more conclusion, and in time, the mechanical inclination he had displayed as a boy in Grantham began to work out a new way to view the heavens, a way free from the distortions created by lenses. It would be this device, built with his own hands, that would bring him to the notice of men outside the small confines of Cambridge. It would draw him out of his self-imposed seclusion into broader conversations with more voices. Voices of men jealous that a poor farm boy so far from their world could overturn it without their help or notice. And so it was that Isaac Newton would first experience scientific engagement, and it would bruise and batter his sensitive soul and draw from him his truly competitive anger.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 3, Finding Our Place. Episode 27.2, Supplemental. Isaac Newton, Conflict and Withdrawal. When Isaac Newton returned to Cambridge in 1667, his work in optics continued. The main thrust of this line of investigation at this point was in looking at lenses, specifically those used in telescopes. If you were to use a telescope in those days, you would have noticed two things. even with the very good lenses being produced by men like Christian Huygens. The first would have been that you couldn't get things to be in focus across the entire field of view of the eyepiece. If you focus the telescope to produce clear images in the center of the field of view, the objects near the edge would be somewhat fuzzy. If you sharpened the objects at the edge by turning the focusing knob, the items in the center got a bit blurry. The second thing that you would have been able to see is that even for objects in focus, you always had a bit of a color halo around the object. You could focus so that the sharp object was a bit reddish, but then it would have a bluish halo, or vice versa. But the halo was always there, and it was especially noticeable the smaller the object got. With the advent of large lenses with longer focal lengths and greater magnifications, the problem only got worse. These two things are known as aberrations, and Newton set out to see if he could remedy them so as to give consistently sharp and halo-free images across the entire field of view of a telescope. Starting from his work with conic sections and Kepler's explanation of how lenses work to magnify an image in a telescope, Newton realized fairly quickly that the first problem had to do with the shape of the lens being used. Kepler's telescope design, the one being used by almost all astronomers at this point, used two converging lenses, or curved pieces of glass, that were thicker in the center than they were at the edge. A common example of this type of lens is that found in a magnifying glass. These lenses were made by using an abrasive material to grind the thick piece of glass to a predetermined shape, effectively shaving off the glass at the edges of the lens. The curve of this shape can be thought of as being part of the edge of a sphere on each side, so that the lens took on the correct shape with two curved sides. What Newton realized is that a piece of glass with a pair of spherically shaped surfaces didn't actually focus all of the light to a single perfect point. Instead, the areas near the center of the lens focused the light to one point, while the parts of the lens out at the edges would focus the light that passed through them at a slightly different point. This is what caused the problem with not being able to get the entire field of view into focus at the same time, and it is known as spherical aberration. What he then figured out was that the correct shape of the lens surfaces should be paraboloids, or, in simpler terms, the three-dimensional versions of those two-dimensional parabolas you may remember from your math class. The reason these hadn't been used was that grinding glass to parabolic shapes was, and still is, a lot harder to do. To solve the problem, Newton set out to create a set of lenses with parabolically shaped surfaces and found that doing so was truly painstaking work. However, with a bit of perseverance, when he was finished, he found that the spherical aberration did in fact disappear. What didn't go away, however, was the other effect. No matter how carefully he worked to shape his lenses, he couldn't get rid of the color halos, something now known as chromatic aberration. It was then that his work with prisms came back to him. In his words, written for a paper he would later submit to the Royal Society, white light was, quote, a heterogeneous mixture of differently refrangible rays, end quote. He realized that as long as he used things that bent the light, different colors of light would be bent by different amounts. This was the fundamental basis for the prism's ability to split white light into different colors. He recognized that the lenses, no matter their shape, worked by bending light, and so blue light would always be bent a little more than red light was. And so if a light source was emanating both those colors, each single lens would focus the light at slightly different distances from the lens. From this, he concluded that a simple telescope based on refracting or bending light would never be free of the problem of chromatic aberration. As an aside here, any modern optical system that uses lenses, whether it be a telescope, a spotting or rifle scope, or a pair of binoculars, has to deal with this issue. After the time of Newton's, solutions were found to the problem of both spherical and chromatic aberration that allowed for the use of spherically ground lenses, but these required either multiple pieces of glass that are arranged to cancel out the effects of both types of distortion or special coatings. Some modern, high-quality telescopic eyepieces will have as many as 6 or 8 different pieces of glass in them to achieve these corrections, making them both heavy and expensive. If you get a really cheap pair of binoculars, like the kind that are sometimes offered as free gifts when you purchase something. You can look at a bright white star such as Sirius near the constellation of Orion and be able to easily experience the color halo effect. So what was Newton's response? His idea was to create a telescopic system that didn't rely on refraction, but instead reflection. It turns out that Kepler's math on telescopic optics can be extended to mirrors very easily, and so replacing the objective lens at the front of a refracting telescope with a mirror at the back to make a reflecting telescope is something that can be done. If you've ever used a shaving or makeup mirror that has the ability to create a magnified image of your face, you've experienced this kind of a system. The problem with this approach, however, is twofold. First is that you still have the problem with spherical aberration unless you shape the mirror parabolically. The second has to do with the quality of mirrors at the time of Newton. Due to advances in glass-making technology by the time of Newton, if you made a lens-based telescope, you could get a high-quality lens that would transmit 90% or more of the light that was incident upon it. Mirrors, on the other hand, weren't nearly as good. Some of the sources I've read suggest that a typical piece of highly polished metal alloy might reflect only 30 to 40% of the light that actually hit it. Additionally, since the metal was exposed to air, it would tarnish fairly quickly, something glass didn't do, especially in the humid environment of the British Isles. Because of this, mirrors would have to be much larger than lenses to get as much light from the sky into the human eye. Finally, because of the way in which metals absorb some colors and reflect others depending on the alloy, images produced by many mirrors were actually monochromatic, as they didn't show colors. Nevertheless, using a small furnace he had purchased for reasons we'll discuss in our next episode, along with a good bit of putty and pitch to set the shape of the mirror, Newton forged an alloy of tin and copper, commonly known as bronze, and used it to construct his reflective surface. He then refined that surface through a combination of grinding and polishing until it shone with a luster greater than that of a newly minted coin. Set in a tube 6 inches long, the working reflecting telescope was startlingly compact and yet had a magnification of about 40 power and reasonably good resolution. The date for the construction of this instrument is somewhat unknown. From what can be pieced together from his notes, Newton may have built his first reflecting telescope and then kept it to himself for some time, testing it to make sure he'd worked out the kinks in the design. We'll post a picture of the telescope, as well as a diagram of its construction, out at the podcast website, thescientificodyssey.typepad.com, if you'd like to take a look at it. What we do know is that by 1669, Newton was using the telescope, which he kept on the desk of his chambers at Cambridge, to make observations of Jupiter and Venus, showing that it delivered images at least as good as reflecting telescopes that were 5 or more feet in length. While not as grand and powerful as some of the monstrous instruments being constructed by Huygens and Hevelius for making precise observations and measurements, it was a wonder of design and ingenuity in both its compactness and its clarity when viewing relatively bright objects. Newton used the telescope for nearly 2 years before anyone outside of Cambridge became aware of its existence. Henry Oldenburg was a man who had lived an interesting life in interesting times. He hadn't started out as Henry, but as Heinrich at first, and then, in the fashion of those Renaissance thinkers who adopted Latinized versions of their name, Henricus. He had come to London as a diplomat from the commercial city of Bremen during the time of Cromwell's protectorate and had fallen in with a number of philosophically inclined men, including Cromwell's secretary John Milton, the Lord Protector's brother-in-law John Wilkins, and the young and inquisitive Robert Boyle. As a diplomat, he had numerous connections, both scientific and governmental, with whom he corresponded, and like Marin Marcinet had done in France with those working on atmospheric pressure, Oldenburg began to develop a network of communication both in the British Isles and across Europe. He spoke and wrote numerous languages. Thus, he was able to make available work being written about science in the vernacular tongues of Europe as well as that discussed in the more scholarly Latin. When the Royal Society came together in 1662, inspired by the posthumously published writings of Francis Bacon, it was decided in the manner of such things that the organization, devoted as it was to bringing together the observations and studies of those engaged in the new experimental philosophy, as it was called, needed a secretary, someone to keep track of both the various pieces of correspondence between members of the society and the announcements from afar of new discoveries and work. Oldenburg, of course, was just the man for the job, and he would make the position his own and shape it for the remainder of his life. Perhaps the most important contribution made in his tenure as Secretary of the Society was the founding and publishing of a regular circular that collected the various reports in one place for all the members to read. Began in 1665 and titled The Philosophical Transactions, Oldenburg's news sheet became what is generally acknowledged as one of the first scientific journals of the modern age. It was in this role as Secretary of the Society and editor of Transactions that Oldenburg first heard of a new instrument making its way around the various workshops and coffee houses of London. Like everyone else, he was amazed when he finally got the chance to see it in person in 1671 and find out that the reflecting telescope, as it was being called, was the product of a young fellow who had recently been appointed to take the place of John Barrow as the Lucasian Chair of Mathematics at Cambridge. Seeing the importance and value of this new technology and hoping to announce its emergence to his readers, Oldenburg took up a pen and began writing a letter to its inventor, the heretofore unknown Isaac Newton. Now, to be fair, while Oldenburg didn't know Newton from Adam, to say that his name was completely unknown would be a misrepresentation at this time. While Newton hadn't published any of his work in physics or motion by 1671, he had been building up a correspondence in mathematics with others working in the field that was bringing him more than a bit of notoriety among the small circle of practitioners in that discipline. As we mentioned, when Newton had returned to Cambridge in 1667, he had been elected a minor fellow of Trinity College. With this came a small salary, a room on the grounds of the college, and use of the library. It also carried with it the requirement that the fellow take vows of chastity and celibacy, and a commitment to take holy orders at an appropriate time in the future. Regular listeners of the podcast will recognize this as a regular feature of the old scholastic universities. A year later, upon the completion of his Master of Arts, Newton would be promoted to Major Fellow of the college with a slight raise in pay and the offer of more spacious accommodations. During this time, he continued his collaboration with John Barrow on mathematics, though he did not share with his mentor his investigations into light and optics, nor even his more secret growing interest in alchemy. In 1668, Barrow passed along to Newton a work by the London mathematician Nicholas Mercator, titled Logarithmotechnia, that duplicated some of Newton's work on infinite series done during his break at Woolsthorpe. So spurred, Newton drafted a paper titled On Analysis by Infinite Series, which he shared with Barrow. The paper showed that Mercator's work to be a special case of a more general class of infinite series Newton had worked out. Barrow, in turn, shared this with a colleague in the Royal Society, one John Collins, but only after Newton had extracted the promise that his name be left off of the paper. Only after Collins responded enthusiastically to the manuscript did Newton agree to have his authorship of it revealed. After this, Collins and Newton took up a correspondence where Newton would dole out small bits of insight while Collins entreated him for more. Collins shared what he had learned with others and developed a way to tease more from the reluctant fellow of Trinity College. By floating the ideas of another mathematician, Collins could get Newton to respond with a statement of one-upsmanship, where Newton had worked out a more powerful method of doing a calculation and or a more general statement of a mathematical axiom. Here we see the reemergence of that competitive streak Newton had shown as a schoolboy. In time, Newton's name was being mentioned in reverential tones around the mathematical community of Britain and beyond, including in both the Netherlands and France. No one knew exactly what he knew, but it always seemed clear that Newton always had an answer to a question or a better way to do something than someone else had come up with. So, the question arises here as to why Newton didn't publish his work. He's got enough in the way of mathematics that he could publish a several-volume book if he wanted, and he knew that the work would be positively received if Collins' assessment could be trusted. Then there's his work in light and optics. In fact, in 1669, when Barrow set out to give a series of lectures on those topics, it was Newton who did most of the editing of the lectures, and did so much work on clarifying Barrow's thoughts that Barrow specifically acknowledged Newton's contributions. Though it should be noted that by the time of Barrow's lectures, Newton's continuing work on the topic had more or less rendered his mentor's thoughts on the matter completely inaccurate. Even if he thought his ideas on gravitation and motion were too incomplete to share, the other work was groundbreaking enough to establish him as one of the greatest scientists and mathematicians of his age. So why not publish? From what I've been able to gather, there seem to be 2 or 3 reasons. The first is something familiar to those who have studied Copernicus's life. Newton, sensitive and desperately fearful of rejection by those he esteemed, was afraid of the ridicule he might face if his ideas were wrong. It was one thing to study a topic for the joy of discovery, and then to share that with a few close friends or colleagues with whom you had a relationship. It was an entirely different thing to put something out there to a bunch of strangers to have it picked at by men who did not know you, and thus who might misrepresent your ideas or disregard your feelings. The second reason, I believe, had to do with Newton's view of acquiring fame and honor, something that had likely been shaped during his growing up under the strict Puritan rules of the Protectorate of Cromwell. In the Sermon on the Mount, as recorded in the Gospel account of the Apostle Matthew, Jesus has warned his followers not to do certain things, specifically the practices of prayer, fasting, and almsgiving, in the public eye, as such behavior would feed human vanity, and the rewards achieved would be temporary, as they were bestowed upon the recipient by men rather than by God. What seems to have been the case with Newton, at least in my reading of some of his comments, is that he extended this restriction to all of the work he did. In a letter to Collins he wrote, quote, "For I do not see what there is desirable in public esteem, were I able to acquire and maintain it. It would perhaps increase my acquaintance, the thing which I chiefly study to decline." End quote. As we will discuss in time, Newton took his religion very seriously, and if he did internalize the broader Puritan interpretation of Jesus' instructions to his disciples, it is very likely that he saw the sharing of his work as something being at least intemperate, if not irreligious. The third reason might have been that Newton just wanted to avoid the public eye. He didn't want to be known. If you think about his experience growing up during the tumultuous years of the civil wars in the Protectorate, being a public figure often ended badly for those who aggressively sought such positions. The events and turns of the Civil War likely taught Newton that keeping your head down and doing your work was the surest way to keep it firmly attached to your shoulders. Fame was a two-edged sword, and more often than not, that sword ended up in the hands of an executioner. Better to avoid, if at all possible, any notoriety. Moreover, even if that notoriety didn't result in negative consequences, it would make demands on one's time. It diverted one's attention from studying the subtle laws of nature, something Newton found sublimely more satisfying than the attention of any crowd of admirers might bestow. Or, at least that's what he told himself. Time would prove otherwise. Now, such an attitude likely strikes my more academically inclined listeners as strange in this day of publish or perish. But at this time, as long as Newton produced work for the insulated community of Trinity College and the wider community of Cambridge University, he would be allowed to remain a part of that community. This was formalized in late 1669 when John Barrow, seeking his fortune among the bright lights of London and the Royal Society, announced that he would be resigning as Lucasian professor. In his place, he recommended his fellow faculty elect Newton to succeed him. This was a lifetime appointment, revocable only in cases of fornication, voluntary manslaughter, and heresy. While the first two won't be an issue, as we will see, the third will present a more formidable obstacle in time. As Barrow transitioned first to London and then, in time, back to Cambridge when he was named Master of Trinity, he remained in contact with Newton and asked if he could take the reflecting telescope to show around a bit. Newton had already shown it to Collins during a meeting in London, and so he acquiesced to his mentor's request, thinking nothing of it. Surely the experimental philosophers of London had grander and more advanced instruments to work with. Thus, he was a bit surprised when a letter from one H. Oldenburg, Secretary, Royal Society, arrived for him in Cambridge, asking to publish an account of the instrument in the Philosophical Transactions to prevent, quote, the usurpations of foreigners. It being too frequent, the new inventions and contrivances are snatched away from their true authors by pretending bystanders, end quote. In the letter, too, Oldenburg shared that the fellows of the society were so impressed with the instrument that they were proposing Newton for election to the body. It is here that we find Newton at a crossroads. Does he maintain his anonymity and decline to be known outside the confines of Cambridge? Does he follow Barrow to the hustle and bustle of London, recovering from the plague and fire, to join the community of philosophers there with all of the possible influence that course might offer? In his response to Oldenburg, he wrote, quote, I was surprised to see so much care taken about securing an invention to me, of which I have hitherto had so little value. And therefore, since the Royal Society is pleased to think it worth the patronizing, I must acknowledge it deserves much more of them for that than of me, who, had not the communication of it been desired, might have let it still remained in private, as it hath already done some years. End quote. In other words, I'm a bit surprised that everyone's making such a fuss about the telescope. But if you guys think it's worth talking about, then who am I to say otherwise, even if I didn't really think it was all that big a deal? Yet, after a couple of weeks of ruminating, Newton's ego began to assert itself. In a follow-up letter he wrote, quote, I am proposing to them to be considered of and examined an account of a philosophical discovery which induced me to the making of the telescope, and which I doubt not but will provide much more grateful than the communication of that instrument, being in my judgment the oddest, if not the most considerable detection which hath hitherto been made in the operations of nature. End quote. Again, to paraphrase, if you think the telescope's interesting, wait until you find out why I decided to make it in the first place. That'll really blow your minds. Oh, and since you brought it up, what exactly does being a fellow of the Royal Society entail? Newton had cast the die. Letter from Newton to Oldenburg, to be read at the next meeting of the Royal Society and published in the Transactions, arrived in London in February of 1672. In it, Newton presented both his various investigations on light using the prism and, more provocatively, what he called the theory. The experiments he shared were those wherein he had shown a thin beam of sunlight through a triangular prism and had seen the light reflected or bent into an oblong rainbow, as we discussed last week. This result, in and of itself, was surprising, as most previous experiments of this sort, including those done by Descartes, had reported the refraction to be circular in nature. This streak of smeared out color, now called a spectrum, was observed on a wall some 22 feet from the prism, covering an area of 2 5/8 inches wide by about 13 1/4 inches long. To be clear, this was and is a fiendishly difficult bit of experimentation to do. The sun, measuring just a bit more than half a degree in the sky, is, as we have said, in constant motion. As such, so is the beam of light coming from the hole in the curtain that covered the window first in Newton's home in Woolsthorpe and then in his chambers in Cambridge. To get a better picture of this in your mind, imagine shining a flashlight beam through a door that is just ever so slightly open, and then moving that flashlight from right to left. The sliver of light that enters the room and shines on the other side of the door will move across the opposite wall. With the sun's motion, Newton could only examine the rainbow, or spectrum as it was called, for a few moments before the apparatus had to be reset. Later, when others tried to replicate Newton's work, they often failed in the attempt, something that would lead more than a few to doubt the veracity of his results. He then reported that this led him to what he called his experimentum crucis, or the crucial experiment. This, by the way, was a phrase he had taken from Hooke's writing, the latter natural philosopher having adapted it from Francis Bacon's Instin's Crucis. In either case, the phrase referred to a piece of evidence that decided between two competing explanations. Bacon had taken it from the legal realm and inserted it into the growing discussion about the establishment of scientific facts in the early 1600s, and Hooke had applied the concept to controlled experiments or observations that would allow for the experimentalist to determine between competing hypotheses. In this instance, Newton's crucial experience was to isolate or separate a beam of light from just one part of the spectrum, either red from one side or the deep violet color from the other, and pass that through a second prism. In doing this, he was able to determine two things. First, a single color beam could not be separated into more or further colors. Second, the violet beam was bent at a greater angle than the red beam. For Newton and many others who heard or read these words, this was a thunderbolt. The conclusion could only be that white light was made up of many different colored rays that were bent by glass by different amounts. This refraction showed that color was not an alteration of light, but rather a fundamental property of it. White light was, he said, a mixture of all of the different colors. He then went on to say that if all of the colors were mixed back together through the use of additional prisms, the result would be, once again, to arrive at white light. The prism did not create the colors as some had claimed, but rather it had separated them. Finally, since all lenses were made of glass that uses this property of refraction to focus light in a telescope, no system constructed of lenses would ever be free of chromatic aberration. Hence, his construction of the reflecting telescope, whose appearance in London had prompted the communication. In this first part of the letter, one sees a communication style that is much like the personal narrative of Kepler, but alloyed with the abstraction and theatrical construction of Galileo's dialogues. While the debate between the various dramatis personae found in Galileo's work are missing, there's no mistaking that Newton was organizing his account to lead the reader to a climax of discovery that likely diverged from the actual investigations in that it left out the false starts and wrong turns so common in Kepler's style of narrative. It was, in essence, the work of 6 years condensed into half a lecture, while still seeming to bring the listener or reader into the moment of discovery and continued investigation. In his letter, both in the description and the following hypothesis, it is clear that Newton owed a debt to Kepler and Galileo in other ways as well. Following the work of Kepler, and in contrast to others, Newton uses the German mathematician's ray description of light, one found in physics and optometry textbooks today under the heading of geometrical optics. Moreover, he asserted that optics, as it related to light and color, could be established within a Galilean mathematical framework of abstraction and certainty. Things were no longer to be conjectured, but established through mathematical deduction based on observation. And if that weren't exactly the case in the present time, Newton believed that full understanding of the phenomena would come through that path. The second part of the letter works from the experimental results and conclusions drawn from them to speculation on the nature of light itself. Put another way, Newton offered up his thoughts on the question, what is light? To be clear, Newton never completely pinned himself down on this, but his suggestions offered a clear break from those who had gone before him. Descartes had put forward a hypothesis that light was a sort of pressure in the ether, that fifth Aristotelian element that Descartes believed permeated all creation rather than just the regions of the cosmos above the lunar sphere. These pressures caused the corpuscular vortices of the ether to rotate, which led to different colors. Hooke, for his part, had disagreed with Descartes and offered up a competing view in the Micrographia that described light as vibrations in the ether, much as sound was a vibration of the air. This explanation would be shared by Christian Huygens, who would develop it far beyond Hooke's ideas into a fully fledged explanation that accounted for a variety of different optical phenomena. Newton, though, rejected both of these explanations and suggested that light be viewed as a stream of corpuscles in motion through the ether. The reason he rejected Hooke's vibrational theory was that, unlike sound, light did not seem to evidence the phenomena of being able to be bent around corners. Instead, he countered that light consisted of globules that traveled at finite speed and impinged on the eye to produce images as had been described by Kepler. This was a provocative set of conjectures, and it immediately set off a firestorm of controversy that would last nearly 4 years, until Newton more or less removed himself from the continued scientific discourse on the topic. In that time, 10 articles in response to Newton were published in the Transactions, and he wrote 11 responses himself. All of this was mediated by Oldenburg, who walked the fine line between allowing for and encouraging active discussion of a relevant scientific topic, and assuring Newton that just because there were those who disagreed with either parts of his work or his suppositions, that he was still held in great esteem by the society. Newton's foremost critic was Hooke, whose idea had been most directly challenged. Hooke, by this time, had the official title of Curator of Experiments for the Royal Society, and he told Oldenburg and other fellows that he had done the experiments Newton described hundreds of times. Now, whether this was true or not is a matter of some skepticism among historians of science, but he did credit Newton for the subtlety of his observations. His objection was to Newton's conclusions that color was a property of light rather than something imparted upon it by the prism. Though Newton had claimed his work contained the experimentum crucis that decided the matter, Hooke contended that he was not convinced. He argued from analogy with sound, wherein the air did not contain the sound, but rather was given it by the action of, say, an organ pipe or a violin string. Therefore, he saw no benefit for setting up and demonstrating Newton's work before the assembled society. In publishing this response, Hooke was not only questioning Newton's interpretation of his results, but whether he had conducted them competently, and this really deeply offended Newton. His response was a blistering critique of Hooke's criticism. First, he excoriated Hooke by name for not bringing up his concerns regarding Newton's methods in private correspondence before taking the matter public in the pages of the Philosophical Transactions. In this, while probably overreacting a bit, Newton had a point. Second, he expressed his frustration that Hooke's rejection of his claim was, quote, a bare denial without assigning a reason, end quote. In other words, he felt like, Hooke was just sort of saying, this is wrong, and I don't have to tell you why. He then went on to bring forth an example after example that supported his interpretation, including some of Hooke's own field of claimed expertise, that of microscopy. In these responses, Newton implied over and over that Hooke had not actually done the experiments, and that his questioning of them was founded in this ignorance. As we have said, Newton may well have been correct in this charge, and his response seems to have answered most of Hooke's doubts, with the exception of those related to the nature of light. In this, Newton repeated that in his suggestion of light being made of streams of particles, he had very carefully and intentionally used the word perhaps, thus separating established conclusion from speculation. Newton's other notable critic was Christian Huygens. While Hooke was the most vociferous in his attacks, Huygens was a great deal more capable in his questioning of Newton's conclusions. As his version of a vibrational theory of light was much closer to the full wave theory we think of now, he could muster a fuller and more rigorous set of counterexamples than Hooke had. As a point of clarification here, it should be noted that at the time of these correspondences, waves were things that only happened in water. As such, the natural philosophers of the time had a difficult time transferring the ideas and techniques that applied there completely over to other phenomena, preferring to think in terms of vibration or oscillation in those cases. Huygens would make great progress towards applying wave ideas to light, and, as we have said, he was able to point out issues with Newton's explanation much more ably than Hooke had. Newton's response was filled with frustration and blunt talk, something Huygens, more used to the measured tones more often found in diplomatic and scholarly discourse, found jarring and really quite distasteful. While Newton would write Huygens privately to apologize in a fashion and explain the reason for his brusque response, relations between the two men would remain cool and distant, though Huygens, in a bit of a peace offering, would send a copy of his work on clockmaking, Horologium Oscillatorium, to Newton. Newton's response was, in turn, graceful and full of praise. While the hatchet was being buried with Huygens, Newton also decided to end controversy with the Royal Society by writing to Oldenburg in 1673, just 15 months after his work had been published, that he wished to withdraw his membership and terminate further correspondence. Writing to Collins at the time, he said, quote, "I suppose there hath been done to me no unkindness, but I wish I had met with no other rudeness in some other things. And therefore I hope you will not think it strange if, to prevent accidents of that nature for the future, if I decline that conversation which hath occasioned what is past." End quote. While Oldenburg begged him to reconsider and assured him that he was still held in very high esteem by the Society, he only managed to keep Newton from leaving the group by waiving Newton's dues, in effect keeping him on the Society's roll through no activity on Newton's part. In Newton's mind, he had ventured forth from his enclave at Cambridge and had offered the wider philosophical community a glimpse at his work, and he had suffered because of it. He had revealed a deep truth regarding the natural world and had been disputed by men who he didn't even know except by second-hand reference through Oldenburg's publication. He had shown how science could be rooted in the actual data of direct observation, something ensconced in the Society's charter, and he had been rebuked for challenging grand theories based on little more than supposition. He had offered up his investigations for consideration, and in doing so, he had sacrificed his tranquility. Yes, he had acquired some fame, but the glare of the bright light had hurt in a way that even the sun had not, back in his experiments at Woolsthorpe, and so he retreated to the anonymity and safety of Trinity College, Cambridge, to pursue his own thoughts and researches undisturbed. In his response to Oldenburg's plea that he remain active in the Society's work in spite of the criticism that had been leveled at him, he wrote, quote, "The incongruities you speak of, I pass by, but I intend to be no more solicitous about matters of philosophy, and therefore I hope you will not take it ill if you find me ever refusing doing anything more in that kind." End quote. Following this, his correspondence ceased for the next 2 years. In 1675, things changed for Newton. His investigations in alchemy and a matter related to his position at Trinity, topics we will address in our next episode, necessitated that he travel to London. While there, he met with the members of the Royal Society that had, for so long, only been names and words, supporters or enemies, allies or antagonists. The most important meeting he had was with Robert Boyle, a fellow believer in the arts of alchemy and a devout adherent to the idea that matter was made of atoms. Boyle, the consummate gentleman, greeted Newton warmly, in contrast to the hostility Newton felt he had encountered from Hooke and others. The two men talked shop on topics ranging from various experiments to be done with Boyle's now famous air pump and vacuum chamber to what forces might be responsible for the adherence of one atom to another. This meeting re-engaged Newton with the intellectual world outside of Cambridge, and he began working on a manuscript to share with other philosophers that he titled Hypothesis of Light. Here, we should note that Newton's relationship with the word hypothesis was a complex one. When Hooke had used it in reference to his work in 1672, he had taken great offense, as he believed that his conclusions had a nearly mathematical certainty to them as they were deduced from his observations. In this, he was thinking as a mathematician, where hypotheses were the least of ideas. By 1675, however, perhaps as a result of his conversation with Boyle, who understood the difference between the new experimental philosophy and mathematics better than most, Newton had embraced the term, understanding now that in this new way of investigating nature, it offered up a path for new research. In the hypothesis, he fully expressed his corpuscular theory of light, with a host of attendant evidence to support it. He understood, however, that this evidence, as strong as he felt it to be, did not amount to a mathematical proof or demonstration of the idea. As such, in a bit of rhetorical wizardry, he asked the reader to allow him to speak of the idea as if it were true, work out the consequences, and then see where that led without involving him in the never-ending objections and debates that his last submission had engendered. He was, in a sense, asking for a suspension of disbelief in order to put the ideas out there for serious consideration on their own merits, rather than as ideas that could be attacked on the basis of other tightly held theories. The manuscript, when sent to Oldenburg, contained the instruction that Newton was giving permission for the paper to be read to the membership of the society, but not to be published in the Transactions. He wanted the society to consider his ideas and then move forward, not get endlessly bogged down in debating with him. When, in December of 1675, the hypothesis was read, it developed a picture of matter that challenged the Aristotelian belief that the stuff of creation was infinitely divisible. While Newton acknowledged that the constituent building blocks of nature were smaller by at least a factor of 1,000 than was accessible by the microscope, he, like Democritus of old, argued that many phenomena could best be explained with the assumption of a corpuscular theory of matter. The most astounding of the various experiments he recounted in support of his ideas was the enclosing of a metal disc within sort of a glass envelope or shell. The glass had then been rubbed rather vigorously with cloth. When the disc was then brought near some bits of paper, they began to dance. He wrote in the paper, quote, "Sometimes leaping up to the glass and resting there a while, and then leaping down and resting there, then leaping up and perhaps down and up again, sometimes in lines perpendicular to the table, sometimes in oblique ones, and turn off and about so nimbly as if in the midst of a whirlwind." End quote. In other words, he had shown a new electrical system, and he had found that he could not explain the behavior of that system in terms of Descartes' mechanical philosophy with matter pressing on other matter. Instead, he offered up the idea of ether as sort of a transmitter of force. It was a way of saving what he could not explain without resorting to occult forces or mysterious actions at a distance. In time, he would abandon this artifice. This idea, though, at this time, would infuse almost all of his thinking of this period, as he tried to work towards a unified explanation of the various processes of change he saw not only in the world outside his set of rooms at Cambridge, but also in the secret furnaces where he practiced the most forbidden of arts. Soon, his words turned to the main topic of the communication, that of light. In it, he credited Hooke, who would have been in the audience, with an observation of the interaction of light at the edge of a razor. We now know this to be the phenomenon referred to as diffraction, but the observation was new, at least to the listeners in most cases, in 1675. Hooke had suggested that this bending of light at a sharp edge, say that of a razor, was possible proof that light was a vibration, as it showed that in certain circumstances light could go around corners just as sound did. Newton wasn't sure if this was the only explanation, as he thought it might represent another form of refraction, but he did call Hooke's work a noble invention. And so, was this the long-awaited rapprochement? Were the two men going to make up? No. With the skill of one who had long savored this moment in his imagination, Newton slid the knife between Hooke's ribs. In the paper, he recalled that he had read of the experiment before Hooke's 1675 account. What was it? Ah, yes, the French Jesuit, Henri Fabry, had discussed it, and hadn't he, in turn, heard of it from the Italian mathematician Grimaldi? So maybe it wasn't Hooke's discovery, after all. Now, can you imagine Hooke's anger in that moment? Sitting there with all of his peers, called out in a letter from a man 50 miles away in Cambridge who couldn't find the courage to face him directly. It's just incredible the animosity these two men had for each other. Hooke had made an enemy back in 1672, and now Newton had poured gasoline on the fire. After the reading, Hooke had gathered friends and colleagues in one of London's many coffee houses, and he began to spin the tale that Newton had stolen his new hypothesis from Hooke's work in the Micrographia. It was a claim that Hooke would repeat to the entire society at its next meeting, claiming that Newton had merely extended the work in certain areas. Oldenburg, who had grown to dislike Hooke, made sure Newton heard about Hooke's charge. In response, Newton set out the chain of logic and priority and showed that Hooke had merely repurposed Descartes' work, while Newton's thought was original beyond the fact that both men had invoked the Frenchman's ether. By the end of the letter, Newton claimed to have destroyed all Hooke had said. In the true analysis of the hypothesis, however, and in the resulting letters, it is true that Hooke really was onto something. Newton wasn't really sure what light was. He wanted to talk about both particles and vibrations in the ether, while not really committing to either. It was an ambiguity that would bedevil scientists until Niels Bohr, Werner Heisenberg, and Wolfgang Pauli would develop the Copenhagen Interpretation of quantum mechanics in 1926 that accepted that the way in which you looked at light determined how you saw it. By the way, if you're interested in learning more about this development of human thinking, I would encourage you to listen to our episodes from Season 2 of the show. Oldenburg was convinced enough by Newton's letter, and tired enough of Hooke's taking credit for everything someone else in the society had ever thought about, that he had Newton's letter read aloud at the next meeting in response to Hooke. Once again, Hooke was humiliated, and once again he took to his coffeehouse group to plot strategy. This time, however, something was different. Whether his friends sat him down and told him that to continue along this path would just result in him looking worse and worse, or if they convinced him that you attract more flies with honey than vinegar, Hooke decided to take the conversation private. A good way to think of this is like one of those escalating debates you see on Facebook. Well, one person is sort of thrashing another in the comments thread for something with well thought out and logical arguments, but the other person just won't yield. Not at least until a couple of that person's friends comment that the first person has made some really good points and that, maybe they ought to consider those. Then the second person decides to send the first person a conciliatory message saying, well, maybe I can see your point, etc., etc. That's exactly what Hooke does, adopting a humble and philosophical tone to seem like the bigger man. He, of course, undermined this by immediately saying in the letter that he suspected that others were misinforming Newton about his intentions, something he claimed to have had prior experience with. In other words, he says, our beef with each other isn't really my fault in any way. Others were just talking crap about stuff, Hooke then went on to praise Newton's work and claimed that they both were in pursuit of the same thing, the discovery of truth. Newton, however, saw through this bit of flattery. But he also understood that if he wanted to disentangle himself from the ongoing conflict, he could accept Hooke's offer of reconciliation. Thus, in response, Newton wrote back, calling Hooke a true philosophical spirit and hoping that the two could continue a private dialogue on matters of mutual interest. It is in this letter that one of Newton's most famous quotes can be found in the form of faint praise and perhaps aspirational sentiment. He wrote, quote, what Descartes did was a good step. You have added much, several ways, and especially in taking the colors of thin plates into philosophical consideration. If I have seen further, it is by standing on the shoulders of giants. End quote. I say perhaps here because the promised correspondence never actually materialized. The line would go dead for the next 2 years, and when Hooke wrote again, it was out of desperation and on a completely different topic. Why was this? Maybe it was due to the fact that the two men were looking for a way out of what had escalated into a scandalous situation that had become the subject of gossip at London parties. Maybe it was that they both had better things to do than to argue about a difficult-to-prove hypothesis. Maybe, though, it was something a great bit more personal and spiteful on Newton's part. As many of the commentators and authors I have read have pointed out, Newton's praise and aspiration of standing on the shoulders of giants can be understood in a very different light when one knows that Hooke was a hunchback. This brings us to a good stopping point. Newton is back at Cambridge and will not re-emerge again for some time. This, however, does not mean that he wasn't working or thinking. Next week, we'll take a look at the two topics Newton wrote most about, topics that might have gotten him sent to the gallows had anyone known about them and cared enough to do anything about it. Between now and then, if you've got a minute or two and you're enjoying the content of the show, please share it with whatever networks you think might benefit from knowing about our journey. Also, if you haven't done so, please subscribe to the show on whatever service you're using, and if you can, and I know a lot of the apps don't exactly make this easy, please leave us a strong review. If you're looking for ways to connect with us, you can like our Facebook page, follow me on Twitter, my handle is @ChadDavies, or send me a note at cldavies@mac.com. Also, on one other note, if you aren't listening to Peter Adamson's excellent podcast, The History of Philosophy Without Any Gaps, I would encourage you to go out and check out his 14-minute episode on philosophy and the recent political events in both the United States and Britain. I think Mr. Adamson offers some excellent advice for everyone who is wondering how to navigate through these currently fairly choppy waters. As always, thanks for being a part of the crew, and until next time, full sails on your journey.